Chris.
I'm Peter.
I'm Adam Capdeville.
I'm Avery Brunk.
I'm Hunter Bilby, and this is the comparisons of reduced order models. This is a diagram of the simulation in which our data was collected that we got from Dr. Lutman. Each dot in the image represents a sensor that picks up the radiation of the simulation. The boxes on the plane are steel boxes that are there to introduce some interference for the centers. It's a 21 by 21 grid of detectors measuring radiation from a source at the center. On this slide, this is the photon energy spectra that we get from graphing each respective element. Cobalt-60 has two signature peaks at 1.173 and 1.322 mega electron volts. Cesium-137 has a peak at 0.662 mega electron volts, and technetium-99 has one subtle peak at 0.147 mega electron volts. Each spectrum is composed of 200 points on the y-axis, and the total size of our dataset is 200 by 1764.
This is our PCA component analysis abstract. So principal component analysis, or PCA, is a dimensionally reduction method that is often used to reduce the dimensionality of a large data set by transforming a large set of variables into a smaller one that still contains most of the information in the large set. Reducing the number of variables of a data set naturally comes at the expense of accuracy. But the trick in dimensionality reduction is to trade a little accuracy for simplicity. Because smaller data sets are easier to explore and visualize and make analyzing data much easier and faster for machine learning algorithms without extraneous variables to process. So to sum up, the idea of PCA is simple. Reduce the number of variables of the data set while preserving as much information as possible. Now, here is how our data broke down with PCA. Most of the data is just background radiation, so it makes sense that PCA of 1 explains 95 or greater % of our data, saying that there is background radiation here, but you can see mostly on the right that through our components 3, 4, and 5, 3 being our cobalt peak, which is the blue, and then PCA4, which is our cesium, is our orange peak right there, and our PCA5 is our tech peak, which is the green peak right there.
So non-negative matrix factorization, or NMF, is our second reduced order modeling technique. NMF NMF is a feature extraction method that allows us to decompose our original data into the matrix product of two matrices, W and H. In our case, we reduced to 4 features, which decompose our original 200 by 1764 data matrix into a 200 by 4 W matrix and a 4 by 1764 H matrix. So here we take a look at those 4 features by graphing the individual columns of W. First column here again, we see the dominant background radiation, but columns 2, 3, and 4 gave us clear discernible peaks for Tech-99, cesium, and cobalt. The H matrix gives us each feature's weight. So by graphing the rows of H, we're able to see each feature's activity across the grid. Row 1 gives us, again, that strong background radiation that disperses along the shielding, but rows 2, 3, and 4 show most of the activity coming from the center and decreasing as it gets further away, which makes sense because the radiation source is located in the center of the grid.
First, to understand tensor decomposition, you have to understand what a tensor is. A tensor is just a way to organize data. It's a multi-dimensional array. So a tensor of order 1 would be a vector, a tensor of order 2 would be a matrix, and in our case, a tensor of order 3, it basically is a cube of numbers. To get a tensor of order 3, you basically add up all of the tensor rank 1 tensors, which will get you your tensor of order 3. In our case, the tensor decomposition is going to pull out the behavior that occurs in each dimension of our tensor. So the first would be the box component, the second would be energy give off, and the third one would be our sensor component. And all tensor decomposition does is the sum of outer products of that vectors in order to reduce the order of the whole tensor. Our first factor is the behavior across boxes. And yes, it looks like a bunch of triangles. So as you can see, if you look at our green line, for instance, there's a signature peak at box 2. In our case, box 2 is cobalt. So that means that in that source, the main source in that would be cobalt. So it goes from no background to 100% cobalt to no cesium, and then to no tech, which shows the specific cobalt line. And this can be repeated for our tech and for our cesium, as well as 2 lines that are kind of a combination of both, which can be factored to the background lines. Our next factor is the behavior across the energy sources. So what this was able to do, the first 2 graphs, they show the background noise that is very present in our data. And the second 3, they are able to pull out the signature energy peaks of cobalt, and then the 4th column pulls out the cesium, and the 5th column pulls out the tech. And finally, factor 3 would be the behavior across sensor number. Like Chris said when he was talking about NMF, the background noise, it's present in all of our data, so there's not really a signature peak. But for cesium, cobalt, and technetium, we see the signature peak in the center, and it fades out when it gets farther away. This is once again because the source of our energy was placed in the center of the 21 by 21 array of sensors.
So the order that we've presented these in, starting with PCA, then following by NMF, and lastly CPT, is the order of increasing amount of information that these methods have given us while reducing our data. Computationally, PCA is the most efficient and happens the most quickly, but also gives us the least unique information. NMF is, it runs computationally about as quickly as PCA. And CPT, in order to give us the 3 factors, takes about 48 minutes of computation in order to break it down into a deconstructed tensor. One thing that we did for each method was to calculate the L1, L2, and Frobenius norms of our data before and after deconstruction, and then take the difference of the 2 in order to quantitatively describe how accurate they were at retaining as much information as possible from our data. We see here highlighted in yellow that the L2 norm, the difference between the 2 L2 norms for PCA, is on the order of 10 to the negative 13. And NMF for the L1 norm and the Frobenius norm, these are on the order of 10 to the negative 7 and 10 to the negative 8, respectively. But generally, with the exception of the L1 norm and the Frobenius norm in PCA, they are all of 10 to the negative 7 or below.
Thanks for watching.
Right, and here's our references.
And here you go.